morning. My name is James Reinders. I work at Intel. I thought it'd be a cool place to go work for a few years. I hope you have as good a fortune as I did. I have been there for 25 years, not what I expected. It's a great place to work, and during that time, I've gotten to do some fun things, including I was an architect on ASCII Red, which was the world's first teraflops machine, which doesn't sound so impressive now. But as we rush towards exascale, I'm hearing the same things again. What will we ever use that much compute power for? It's probably more than the world needs. No one can program it. We said the same thing about teraflops, if you believe it. But in any case, it's my pleasure. I work out of Portland, Oregon, and the other gentleman, Jackson, that'll be talking a little later from Intel, works just 3 hours south of here, or 2 hours if you drive like he and I do, in Champaign-Urbana. This is the dry, I'll talk about computer architecture, what it means, and so on. The speaker before me already said everything you need to know. If you could parse all of it and handle all the implications, you can just go home. Hopefully you'll hear some of the same themes, but I thought I'd do something a little different. I can talk to you about detailed computer architecture, and I will get into it and make some observations and so forth, but I'll start by saying the real challenge, I think, as a programmer is to do what I would call see the forest. So there's a cliche about someone missing the big picture. In English, the cliche is not being able to see the forest for the trees, or not being able to see the forest because of the trees. And I would say the same thing's true of programming and computer architecture. A lot of times we find people writing the code too hard towards the architecture itself and losing track of what they're trying to accomplish and what the long-term implications of that are. So don't get me wrong, I love computer architecture. I can go on and on about computer architecture. I'll take you down to the bits, so feel free to interrupt me and ask me a detailed question. I can get very enthusiastic about why we put a particular instruction in, or why we designed this, or why we're integrating that into the silicon, or why we run at one clock rate versus another and choose how many pipelines to have. But I've got a challenging question, and that is, can you actually teach parallel programming without first teaching computer architecture? So I got out at home. I've got a stack of parallel programming books that if I set on the table would be at least this high. And I actually, while preparing to work on a book, I kind of as a joke, and I actually lost the email, but I put an email together and I went through the books and estimated how many pages of the book were spent talking about computer architecture and APIs, which is a different topic, versus actually telling you how to program. And all the books I had, classic books in parallel programming, spent more time teaching computer architecture than programming. I also took a stack of books like Thinking in C++ and How to Program in Fortran and stuff and did the same thing. And when you teach someone to program in Java or C++, you don't spend a whole lot of time talking about computer architecture. So I think that's going to change. And we were fortunate enough to secure enough books for everybody here of the structured parallel programming book, which I'm going to reference a few times. We're starting to use it in some classrooms. One of the things we really worked hard on this book on is to not fall back on teaching computer architecture or talking too much about it, but rather talk about what works. And one of my favorites is we have a whole chapter on stencils. If you don't know what a stencil is and how and when to apply it, you're not a parallel programmer. Well, why would anyone not know what a stencil is? Well, because we just actually don't teach it. You just sort of pick it up on the job. We have a chapter on it in here. It was actually a sub-chapter until we went over our outline a little more carefully. We do map and reduce, and I'll talk about some of those later, but understanding the techniques independent of computer architecture. So I'm going to go back to this a few times about how do we do this. And for me at Intel, it's a huge challenge. How do we design our machines so that we keep them programmable? And what is programmable? Do we really want to teach a lot of computer architecture as the only way that we can teach someone to use a machine? So what are some trees? So we could talk about cores, hardware threads, hyper-threading, and other types of hardware threads, vectors, offload, heterogeneity, cloud computing, caches, NUMA. I'll probably mention more than half of these during my talk. These are the trees. And if you spend your time writing your program because you know how many cores you're targeting, or writing it because you really understand the vector architecture of the machine you're on, you are probably doing yourself a disservice. And you will work on codes, if you haven't already, that are 20 years old. Please don't be the person that's creating the code that's being cursed in 20 years because you didn't understand how to keep it independent of the machine. So to me, the forest comes down to two things: parallelism and locality. There's many, many ways to say this. Understand where your parallelism is and express it, and understand data locality, data movement, data this, because frankly, as was already mentioned this morning, flops are cheap. Flops are the things you can throw at your problem in excess, but moving data around even a little bit is going to cost you, both power and time. So I could go through all these and give you specific things, and I will during the talk. Use task, use SIMD, targets. In fact, I'll dive into SIMD usage after the break. Explicit vectorization, which is a very interesting topic these days. But I'll just bring it back to our job. Our job as programmers, I like to keep things really simple, and then this is complicated enough. We could spend a couple of weeks studying this, which is, I think, what you're going to do. Figure out where a parallelism is in your program and how to express it in as generic of a form as possible while still getting your performance. And increase your locality of reference. Understand the data and how it's being moved around. Unbelievable that just a few years ago, someone wrote a better matrix multiply. Some work out of UC Berkeley. They asked a grad student professor there, said, hey, flops are cheap. I wonder if matrix multiply, if we rethought it, whether we do it different, if we were trying to minimize communication. And by golly, the person came up with an algorithm that used more flops. It failed the test that the speaker before me was mentioning. We used to just count how many flops did our sort algorithm take, how many flops did matrix multiply take. They reinvented it, and now this is the gold standard for matrix multiply. We thought matrix multiply had been overanalyzed and implemented too often. There wasn't any opportunity to improve it. I'm here to tell you that basically every algorithm out there today can be reinvented if it understands these two things, parallelism and locality, better. Now, parallelism, I'll say the asynchronous nature of parallelism, trying to make sure that you aren't making assumptions like I can do this block of code in a certain amount of time. Just as the speaker before me was saying, chunk it up into equal parts. And I think I felt like he blamed it a little too much on the hardware. Yes, our hardware does speed up and slow down and so on, but guess what? Your code doesn't run in the same amount of time when you think it does. You'll do things that are a little different, even though you tell me this section of code always runs the same amount of time. So anyways, parallelism, locality, reference. Well, so this is your mission. This is our mission as programmers. But let me get back and talk more about architecture. You could ask, why so many cores? I ask myself that question sometimes too, but I love it. I love computer architecture, so we'll put as many cores on a die as we can reasonably figure out how to help you use. It wouldn't be a talk from Intel if I didn't mention Moore's Law. So Gordon Moore was one of the founders of Intel, and I've had the good fortune to have met him a few times early on in my career at Intel. This piece of paper is in the Intel archives, and it's revered. It's actually the little drawing he sketched before he wrote his itty-bitty article that then somehow becomes Moore's Law. He was simply observing that technology was moving at a rate that we were able to integrate about twice as many components into the same area of silicon about every 18 or 24 months. Moore's Law continues. It's been a driving force in the industry. By the way, Intel is a manufacturing company. A lot of people say we're a microprocessor company, but Intel was founded to produce DRAMs, dominated the market in EEPROMs for a long time, moved on to flash, to microprocessors. Ultimately, what we do is we're a driving force behind helping the industry stay on track to keep Moore's Law going. But what do you do with all these transistors? Well, for a long time, we had this really cool contract with the industry. We could double the number of transistors on a die, And it turns out that when you double the clock rate of a processor, you roughly quadruple the power consumption. But if you can halve the size of it, you can halve the power consumption. This is really back of the math, envelope math. So if every once in a while we would double the clock rate, but at the same time shrink it to half the size, we could double the performance and double the power consumption. And that seemed like a good deal. I'll give you twice the power for twice the flops. And we were on that line for a long time, but lo and behold, we actually hit limits where people aren't willing to double the power consumption to double the performance. We hit a wall. It's more complicated than just being about power, but it gets blamed on power a lot. And about 2005, microprocessors stopped increasing in clock rate. And this is a plot. I use plots of all Intel processors. I actually have a spreadsheet with non-Intel processors in it, and every time I plot them together in different colors and things, it just makes it more confusing. The nice thing about using Intel processors is they go way back, and it's the same architecture, and so we control how many variables I have on the graph. If I were to plot Spark processors or Power processors or AMD's processors, the trends are the same. It just, if I put them all on one graph, the trends are a little harder to see because they're in different lines. But anyways, around 2005, boom, no more clock rate increases. In fact, more clock rate diversity, if you look at that on the line. But the number of transistors we have, on a die continues to grow. These are logarithmic graphs, by the way. Continues to grow exponentially. That hasn't changed. And I love all the articles on the end of Moore's Law. There always are some. There have been some for 20 years now. Moore's Law is going to end. I agree, every year that goes by, we get closer to the end of Moore's Law. I just don't have any idea when that is. I read an article, 2 articles a few weeks ago. One definitively said it's 2020, and the other said there was some breakthrough that puts it out past 2050. So I don't know. But Moore's Law continues. But what the heck are we doing with it? Well, nowadays, most of it, I would say, is going into parallelism. And parallelism comes in a lot of different forms. One form that parallelism comes in is just handling wider data. So instead of handling one number at a time, we have this creative thing called MMX that could handle several, but it was only 64 bits wide. So, and it couldn't handle floating point. So it could handle 2 full integers or 4 half integers, call them whatever name you give them on your architecture. Floating point SSE, 128 bits wide. Then we introduced AVX 256, introduced AVX 512 recently, 512 bits wide. That's getting hard to ignore. If you can do 16 floating point number calculations in parallel, or 8 double precision, it's getting harder and harder to ignore if your code doesn't use vectorization one way or another. Again, I use Intel examples to be very specific, but you'll find this trend in other architectures as well. No one's ignoring the fact that their transistors can get thrown at data parallelism. And then how many cores? How many hardware threads? This is exploding. Until this century, multi-core chips just weren't significant. They didn't exist for all intensive purposes. But the number of hardware threads per core and the number of cores per die is exploding for a simple reason. We have the transistors. We're not making the cores go faster by a variety of techniques. So what the heck do we use the transistors for? And I'll get to a thing called Pollak's rule. I was amused. I had an internal Intel slide. I didn't even know until I prepared this talk that Pollak's rule was actually externally known. Fred Pollak was a fellow at Intel, and he would always talk to us about different technologies. And then I saw a paper that was presented externally, talked about Pollak's rule, which I'll get to later. And I looked it up, and sure enough, it's on Wikipedia, so it must be publicly known, even though I think some of the editors were from Intel. But this is an architecture track, so let me get let me get real simplistic. And sorry if this looks simplistic, but follow. Hopefully, I'll say some things, I like to keep things simple because when I'm programming, if I don't keep a clear picture in my mind. So in the good old days, the CPU hooked to memory, and the memory worked at the same speed as the CPU, and the CPU started by fetching its instruction from memory and then decoding it and fetching the operands and then writing the results back. Simpler times. Somewhere along the line, someone came up with the bright idea that CPUs were getting faster than memory, and we should jam a cache in there. And you notice I drew 2 lines going to the cache. And this is important because caches aren't just faster. They usually have more ports. They're higher bandwidth. So if an instruction wants 2 operands, most architectures never supported fetching 2 things from memory in one cycle. And you were generally faster if you got 1 out of a register and 1 out of memory. Caches, what they do is they often give the ability for an instruction to grab 2 pieces of data, effectively from memory, but from the cache for the same instruction in parallel. Memories generally won't handle fetching multiple data at once. Now, they fetch cache lines, but they usually only handle 1 request at a time. Now, this may sound arcane because caches are almost always faster and higher bandwidth. That's the way it's always been. And so I can draw a picture, we add more and more caches, and the L1s get higher and higher bandwidth and faster and smaller and closer to the CPU, and the L2 caches have higher bandwidth than the memory, but not quite as high as L1, and they're not quite as fast, but they're still faster than memory. Well, I didn't draw a picture for it, but Intel and other companies are going to start introducing memory caches between the CPU and memory that we call high bandwidth memory. And it's funny how often I say that things like Knight's Landing is going to have some high bandwidth memory, and the press reports it as fast memory. We try so hard as engineers to speak precisely. It's not fast. I never said fast. Now, I didn't exactly announce anything, I hope, but we have never said it was faster than the memory. We said it's higher bandwidth. And yet another thing for us as programmers to wonder about when we're looking at cache hierarchies, there are going to start to be some parts of memory that are higher bandwidth than others. So how do you block your algorithms so that the things that you're really pounding on end up in that high bandwidth memory? In fact, one of the tricks that our operating system groups had to work on as we're designing Knight's Landing, which isn't available yet, is how do you keep the operating system kernel from jamming itself into this memory because it thinks it's so sweet that it ought to put the kernel there and not leave any for the app developer. We have found a way to make the OS stay over in the regular memory and put the high bandwidth for applications. A challenge in several levels. But in any case, caches went like this, and eventually, as Moore's law increased, I was editing my slides a little too much. This should say cache capabilities. It says FP, but cache capabilities were integrated onto the die. Now, some companies resisted. Some architects believe that caches should be external. You could make them better if you kept them external, that these Intel guys want to integrate everything. In particular, some of my good friends at HP kept their caches external for a long time. Even HP puts their caches on their die now. Now, sometimes you have external caches still, so they're not always all integrated. But in general, caches have migrated onto the die because we have more transistors. We can put them there. And they're certainly faster when they're running on the same die as the CPU, and they certainly have more connections, higher bandwidth. Now, along comes floating point. Most CPUs didn't have floating point on them, so we produce a coprocessor. We and everybody else in the industry. Ytech had some fabulous chips. Intel had floating point processors. Everybody did. Coprocessors, starting about the 1970s. These were external, and they talked to the memory in the CPU and did the floating point operations. And guess what? Moore's law, boom, boom, boom. We get more transistors. What do we do with them? We throw the floating point unit on the die. Oh yeah, same time people start thinking, gee, it might be nice to have displays that actually did something interesting. This is like ancient history, right? But along comes GPUs. They have a fixed function to sit between the CPU and the graphics display and do some fabulous things. And as 3D graphics come along, their specialization for that task is outstanding. And one little subtle change that happens, when we put caches on the CPU, the GPU needs to connect not to the memory in CPU, but needs to connect to the CPU to an I/O bus of some sort, because the caches are coordinating activity between the CPU and memory. The GPU needs to have a different access that recognizes and can get the benefit of the caching without having to participate in it. So this is this. And then, guess what? Moore's Law marches along, and the GPUs get integrated. And I'm here to tell you that some people are still resisting this, the assimilation. It's a fun thing. I'm trying to have fun. It's a fun thing in computer architecture to watch the debate, right? It's how much benefit do I get from staying off the silicon versus integrating? But this is an irresistible trend. The Moore's Law, the additional transistors, keeping a GPU and a CPU in a separate piece of silicon is not a long-term trend. You might have noticed caches got put on, floating point got put on, GPUs are being put on. In fact, the world's largest producer of GPUs is? Oh, God. So Intel has been the largest producers of GPUs for several decades. Now, why did you say NVIDIA? Well, because NVIDIA has this design point that they've designed to very aggressively, which is high performance. And frankly, Intel didn't. Intel went for low-cost integrated graphics that was used by the masses. Well, guess what? Our processors have often been designed to that design point also. And it's good for most of the world we do that. It's sometimes as an Intel engineer, you want to pull your hair out and say, we've produced more GPUs, more people wanted to buy our GPUs than anyone else's, but you know what we didn't do? We didn't design the top one. That's okay. Different design points, and it's really important to understand why different products from different companies are different. And it's more often than not, it's an engineering decision, a market decision, than it is a competency level. When you start to think your competitors are stupid, you're probably making a huge mistake. So Andy Grove would always tell us to stay paranoid and assume the competition was always more competent than we wanted to think they were. And he was right. So design points. So we came along with the Xeon Phi coprocessor recently, and the Xeon Phi coprocessor is purpose-built for accelerating technical computing. And I'm going to talk about Xeon Phi today in some detail, and it'll be hard not to sound like an advertisement a little bit, so bear with me. I'll try not to. But what excites me about Xeon Phi is architecture, I think, has gotten fun again. For a long time, what did you put in your computer? An x86. Who did you get it from? Hopefully Intel, maybe AMD, maybe Cyrix, maybe someone else that was imitating. Everyone's imitating the same thing. Well, let's go do something innovative and different. And so GPUs, graphics processing units, getting used for high-performance computing, that's pretty innovative. A little strange, but pretty innovative, reusing something. But I will say over and over again, you're reusing a technology that wasn't purpose-built for that. And I would say NVIDIA's Achilles heel with GPUs is that they're trying to be a GPU and trying to be good at HPC. Now, what's Intel's Achilles heel? We're trying to be x86 and trying to be good for HPC. Well, I'll talk about that. I don't think it's as big of a burden, but I think if an NVIDIA speaker was here, to be fair, they'd tell you it's not that hard to be a GPU and high-performance computing. But it's two different ways of thinking and designing, and I think it's important to understand that if you really want to understand what's driving trends in computers. So what did we do? We built a device and said, we don't care if it's a GPU. We're not going to be a GPU. We're just going to be here to accelerate floating point, HPC, technical computing. And how should we do that? And I'll get into more detail about how we did that. But that kind of sets the architecture that we have. And we've even announced that our next generation Xeon Phi is going to be a processor, not a coprocessor anymore. So guess what? We integrated the many core stuff onto the processor. It becomes the processor. So we can talk about that as well. But let's up level a little bit. So now you have a lot of diversity. And I didn't even put the many core version here. You can have a CPU with some memory. You can have a CPU with something like a Knight's Corner, a Xeon Phi coprocessor attached. You can have a CPU with a GPU attached. You could have a CPU with a GPU integrated, not as common today. The most common node these days in the world is this, a CPU and memory. There are so many clusters out there of different sizes. When you get into HPC, attaching a GPU or a Xeon Phi to provide some acceleration is of high interest to a lot of people and is fairly popular. You don't see the integrated GPU in HPC very much for a number of reasons yet. But these are things you could build nodes out of. And nodes get hooked together. And there's a network interface controller of some sort that sits in addition to the architecture I was showing and hooks everybody together. Now guess what? Make a radical, not so radical prediction. Moore's law will continue. The network interface controllers will get integrated onto the CPU dies as well. And oh boy, the advantages of this, lowering latency, improving capabilities, all sorts of things we can do there. We've announced with our many core Knight's Landing that we'll integrate it, and we've also at least hinted strongly that that'll be part of our CPUs at some point in the future too, without setting dates. But you know what? If you pay attention to Moore's law and how everything keeps getting integrated, it's not exactly a radical prediction that we'll integrate network controllers. And when I say we, yes, I'm from Intel. It means Intel. All of our competitors will too. If they don't, that'd be good for me, but it's not good for them, but they're not stupid. So integration, integration, integration. So a lot of variety. But I'll come back to this. What matters to us as programmers? One is, how do we decompose our problem in parallel to sit on this enormous diversity I just talked about? We program at the cluster level and distribute our problem using distributed memory, things like MPI. How do we program at the node level to understand and behave well with caches, integrated floating point, ultimately integrated NICs? And then how do we deal with locality? I will tell you what, no matter who's designing it, if you're sitting on this node and you ask for data that's on that node, it will take longer to access than if you were using data on this node. And if you understand parallelism, if you just stop everybody and shuffle data and then start everybody up again, that time you were stopped is lost time. You weren't doing things in parallel. So every time you hit a barrier or you do an exchange in a parallel program, you're wasting valuable compute time. So guess what? Reimagine all your algorithms so that can you do your algorithm in such a way that you're exchanging data while you're doing the next step, you get the new data, you incorporate it, you exchange it. If you can do that, you will beat everyone who's doing barrier synchronization and either exchanging data or computing. If you pay attention to your machine and you're either computing or exchanging data or computing or exchanging data, you're wasting one of those resources all the time. Sorry, that's just the way computers are these days. They always have been. It just hasn't been as important probably to squeeze all of this out. So understand how your data is going to move around. Understand how to minimize that. You know, I mentioned stencils before. There was a great paper written a few years ago about the ghost pattern for stencils. If you've ever used stencils, usually you're operating on a local region, maybe of a two-dimensional array, an image, and you keep a halo so that you can do your operations around the edges, and you need the data from the adjacent node, but you keep it. Usually we kept 1 pixel all the way around, or 1 byte, or something like that. And what the authors noted was the bigger halo you keep, the less often you have to exchange data with your neighbors. And so you have to do more computation perhaps, but you do less communication. And they wrote a very nice paper, and I think everybody working in stencils a lot kind of knew this, but they wrote it, and again they were observing, hey, if I kept a little bigger halo, I would exchange data less often. Yes, I was doing more computation, but that fit the role of the way computers are going. So making your programs so that that you haven't carefully measured on today's computer how much computation you can get for communication, but you've thought through the problem more generally, because the trend is CPUs are going to keep getting more and more parallel and faster effectively, and the interconnect's going to look slower and slower relatively. I mean, the interconnects are getting faster. Memory's getting faster. They just aren't anywhere near the pace of a CPU. Amdahl. I can't avoid doing this. Sorry if this is really simplistic, but understanding Amdahl's law and Gustafson's observations about Amdahl's law or Gustafson's law. I hate calling Gustafson's law because it sounds like there's two competing laws. There are different ways of looking at the same problem. Here's my trivial parallel program, or trivial non-parallel program. I want to do 5 things that each take 100 seconds to do. That means it takes me 500 seconds to do 500 units of work. That's a speed up of 1. If I can make some of it run in parallel, I can make my program run faster. So I've got 2 regions. I found out how to put an OpenMP directive around it, run it on my dual core. It runs perfectly, no overhead. And it only takes 50 units a time, 50 seconds to do 100 units of work at the second and fourth steps. So I get a speed up of 1.4. That's pretty exciting on a dual core, or 1.25. If I go to a quad core, I can get a speed up of 1.4. Ultimately, I could throw so many cores at this parallel region that it takes no time at all. It's instant. But those darn serial parts, I still got 300 units of serial work to do out of the 500 units I started with. I have a fantastic 1.7x speed up on a infinitely parallel computer. Darn. Probably wasn't worth the billions of dollars of US taxpayer money I used buying that machine. 1.7 speed up on an infinitely parallel machine doesn't sound very good. You know, and Amdahl knew this in '67. In fact, Amdahl didn't believe very much in massively parallel computing. But he said, if you spend time making part of your program run in parallel, it's not enough. Your effort will be wasted by the stupid serial time. And I'm here to tell you the serial stuff creeps up everywhere. The thing I was talking about before about barrier synchronization, or the speaker before was mentioning about the if you think you've chunked it up into equal amounts of time, but something happens, a denorm number, an ECC action happens, ultimately the best way to do a program these days is to over-divide it and do load balancing to prevent that. But those are all serialism. Anytime you hit a barrier and you wait, you've effectively created a serial portion of your program. But Gustafson came along in '88, and this is after we're building massively parallel machines, and people are still saying that they're stupid because Amdahl's law will prevent us from being able to build a supercomputer that way. Gustafson came along and said, we've kind of noticed that people are building the supercomputers and they are getting useful work out of them. Maybe we ought to figure out why that and Amdahl's law both seem to coexist. And he said, you should look at speed up by scaling up of a problem. So take a look at the problem again, and what if the regions of parallelism, actually what I was using the parallelism for was to handle more data. In this case, on a dual core, I can get a speed up of 1.4 already, and on a quad core, I'm up to 2.2. But you notice I'm scaling the problem. I'm making the problem larger. I can get an infinite-sized machine, and the speed up continues to be linear with the number of cores I throw at it, or the processors. Now, this is an idealistic, never guaranteed not to exceed calculation. Does anybody know, this is a type of scaling. I've got a speed up O of n. This is called weak scaling. Now, I love, when the Democrats and Republicans get together in this country, there'll be progressive taxes. Wouldn't you be for progressive taxes until you figure out that means tax you more when you make more? Or you'll be against death taxes, because that sounds bad, taxing death. But there's another phrase for it, which is inheritance taxes, which sounds more It's all in phrasing. I don't know who had the bright idea that there's strong scaling, which sounds good, and weak scaling, which sounds bad. All weak scaling means is that we can scale as long as our problems keep getting larger. But my observation in this world is our problems keep getting larger. So weak scaling is not something to avoid. So don't run away going, oh my God, I got to go find strong scaling. You're not going to be in HPC very long if the only thing you look for is strong scaling. But you have to understand where your parallelism is. You have to understand this effect. So the parallelism, there's plenty of parallelism there, but the workloads need to grow. You need to understand where your workload can grow. This might be doing finer meshes in a adaptive mesh algorithm. It might be doing better modeling, more detailed modeling in an in-body problem. There's all sorts of things that is more data, but it's very important to know that you're not going to get scaling if you don't get more data. So Xeon Phi. Why Xeon Phi? I was actually looking, when we introduced threading building blocks back in 2006, I did a press event with a bunch of bloggers, and I actually grabbed these diagrams off of there, and it was before it was 4 years before we announced Xeon Phi, and I was talking about trends, and this classic, what I'm trying to draw here is, imagine that that's a piece of silicon. I've got a set amount of area, a set number of transistors. What should I do? Should I put in 8 really big cores, or how many little cores did I put there? 32. Would you rather have 8 cores or 32 cores? And of course, the answer is it depends. Well, what we've been doing more and more with designs like Xeon is trying to be everything to everybody. And we've got amazing things in our architecture, things like out-of-order instruction execution, register renaming, and just amazing buffers and all sorts of exotic cache designs. They're there to make every program in the world run faster, or at least that's what we hope. Whether it be a program written in Java and Python, or it be a server application, an Oracle database, or an HPC application. Serial or parallel. What if you reimagined the design of your computer to say, I'm going to assume it's a parallel program running on me, so I don't care about serial performance. Now, I mentioned I worked on ASCII Red. ASCII Red had 9,200 processors on it. One of the competitors bidding against us was able to do it only with 1,800 approximately, or at least that's what we thought. Should you buy a machine with 9,200 processors or 18? The answer was it either scales or it doesn't, was kind of the answer. The key was how big was it? Our machine was smaller, drew less power, all sorts of things that won because we had a different design point. Xeon Phi is this. Our Xeon processors are that. They're amazingly similar under the cover, except for we made a decision to go with smaller cores that aren't good at serial programs, but they're wickedly good when used together for parallelism. Now, I probably won't dive into this much, but I will tell you, evaluating one architecture over another is a lot of fun. I love when people say, my machine's more efficient because I can do it with less instructions. Okay, but how fast are your instructions? So, the amount of work you can get done in a unit of time depends on how much work you can get done per instruction, how many instructions can run per cycles, and how many cycles can happen per time. And when you look at marketing claims from anyone, including Intel, you can map it into this equation and say, Intel, I'll complain about Intel, but we don't. Hopefully we don't do this too bad, but we do it. We might say, hey, yeah, we can do that in one instruction instead of 2. Well, we just said that we could get more work done per instruction, but we didn't tell you how many per cycle or how fast our cycle time was. So don't get too excited about a claim, because if someone's only telling you they can do one of these different than the competition, they're probably doing the others different in a different way, because we're all engineering using similar technology. I'd like to say I think ours is better, but our competition will say the same thing. We're all worrying, dialing these knobs. Now, I mentioned Pollak's rule. So Pollock's rule basically tells us that we can get if we get 4 times the die area, or 4 times the transistors, we can double the performance in a single core. Or we can get 4x the performance if we go to 4 cores. So if we can do if you give me 4 times as many transistors, generally I can double the performance if I keep sticking with 1 core design. But if I use 4 cores, I can quadruple the performance. What's the difference? Whether you have a parallel program or not. If you've got a serial program, you definitely want me to give you a 2x boost and go away with this whole idea of parallelism. But if we can use a parallel program on it, I can give you twice the performance in that area if I go to multi-core. This is what drives the existence of Xeon Phi. So you can do some math. These are not top bin parts. These are just randomly picked parts by a friend of mine at Intel. And he picked a Xeon, did some math, said, gee, I can do 345 gigaflops with one design. I can do 1 teraflops with the other. One of the designs is has 18 cores on it. It has 2 sockets, 8 cores each. The other one, the Xeon Phi, has got 57 cores. Here's the headache. When I teach Xeon Phi programming, and you'll find one of the books we had is about Xeon Phi programming that Jim Jeffers and I wrote a few years ago. When I was teaching Xeon Phi programming, I was pulling my hair out, and eventually we drew this graph. And I would start the class with this graph, because people would show up with programs with 4 threads and say, I want to run it on a Xeon Phi, see how much it speeds up. We've got a device with up to 61 cores on it, 244 hardware threads, and you show up with a program that knows how to use 4 of them, it's going to suck really bad. And the reason is, a Xeon can run each thread faster. The Xeon Phi has been designed to win the race if you can use lots of them. I'll say the same thing about a GPU. Show up with a program that can only do 4 things in parallel, run it on your GPU, and tell NVIDIA that their part sucks. You can tell Intel ours sucks. When you design something to be highly parallel, you have to take advantage of it. You would think that would be obvious. I think this graph helped make it obvious to everybody that took training from us, but it was really, really important. We didn't just throw the cores on there to look at. You have to use them. So Xeon Phi, up to 61 cores. There's actually, Intel, we don't talk about this much, it's not a secret. There are 62 on the die, but the number of parts that come out with 62 working is the same as when you buy a memory chip these days. The memory chips always have more capacity than they sell to you. They just, the lines that don't work get not used when you use the part. When you start going multi-core, or many-core, some of the cores, it actually has 62. We sell them in 57, 60, and 61 core varieties. Almost all of them, 61. But why 62 and not 64? It's all that would fit. Believe me, we tried. There are limits, optical limits, and when you get outside the optical limits, the transistors show up fuzzy on the die and they don't work as well. So we try to keep sharply focused transistors in the manufacturing process. That's all that would fit. So you're going to see very unusual numbers in the future, I'm sure, with cores. It's going to be how many fit on the largest largest die that we're willing to make. Anyways, let me show you a little bit about what the inside the architecture looks like. And by the way, this is what most processors are going to look like in the future. Xeon Phi is maybe cutting edge at introducing some of these, but Xeon processors now, I don't even remember how many cores you can get. I think at least 16 on a die, but my head spins because the number of cores on a regular Xeon processor keeps going up also. And so they are competition for Xeon Phi, if you will. Xeon Phi has to do something clever inside for parallelism. The number of cores that a Xeon can have keeps going up. But a Xeon design actually looks a lot like this, the newer Xeon designs. You have cores on a ring. And the interesting thing about these cores is none of these cores actually can talk to memory directly. There are things on the ring that can talk to the memory. And each core has an L2 cache next to it. There's actually 512K of L2 cache on each core, and if you do the math, that means you have a little over 30 gig of, did I do that right? Or did I go off a decimal point? Of memory. So you've got, if you can have distinct data in each L2, you have a lot of L2 cache. If you write your algorithm in such a way that every core is touching the same data, you have 512K of cache. So that's because a copy of the data you're using has to be in your L2 cache. But in any case, stuff could be in memory, or it could be in my cache, or it could be in someone else's cache. And there are these tag directories that help us figure out where it is. So if my core doesn't have it, it looks in its caches. If those caches don't have it, they go on the ring and look for it in other people's caches. And if they don't find it, they get it off memory. Well, you don't want to have to go around the ring every time to figure out, is it in this guy's cache, this guy's cache, this guy's cache? The tag directory solves that problem. Otherwise, the performance would be horrible. Anyways, very cool architecture, lots of cores, all connected together by a ring. If we go up a lot more on cores, we're probably going to have multiple rings. I don't know of anybody doing that yet on silicon. It's been done before in supercomputers many times, so it will happen on silicon too. Inside here, the usual things inside the core, the usual things you'd expect in a CPU. Ability to do floating point, ability to do integer operations, all sorts of things. And it's fully x86 compatible. And I get asked sometimes, we get asked a lot, isn't that a horrible expense? Less than 2% of the logic on the core of this roughly 6 billion transistor chip, less than 2% of it is x86 specific. And I said 6 billion, but I probably should have said just a billion or so, because the L2 cache, if you count L2 cache as an x86 thing, I think that's a little strange. Some people will. Then you have to count those transistors against us. But by x86, I mean the compatibility with x86. It's less than 2% of the core's transistors. And the reason for that is the original 8086 was x86 compatible. And it was, I don't remember. It was way less than 1 million transistors. It was in the tens of thousands of transistors. So it cost us tens of thousands of transistors to be x86 compatible, not billions. And vector processing. I'll talk more about what to do with vector processing in my talk after the break. The interconnect. If you love details, these will be good details to remember 20 years from now and think about how primitive this was. The ring is 512 bits wide, bidirectional, that connects these processors. It is wickedly fast. 512 bits routed all over the silicon is a big investment in die area. And we could have fit more cores on it if we made the performance of the interconnect. So it's one of the variables. Xeon cores will probably have lower performance interconnects between their dies, again, because they're trying to optimize to a different design point. We're trying to do parallel programming. We expect communication between the cores, and we have invested more in the interconnect. It's a design trade-off. It's just you only have so many transistors on a die. What are you going to design to use them? On a Xeon Phi, the interconnect's very important. And the tag directory. So we end up with a design that looks like this. A ring, and on the ring are cores with their L2 caches and memory interconnects. This is what I think all CPUs are going to look like until they evolve even further. In the past, CPUs haven't been connected. Cores were initially not connected on rings and so forth, but this is getting more and more common, and I think all CPUs will move to this. And let's see. And caches. So one debate, if you don't know, in the industry is, are caches good or bad? We believe they're good. We believe they're critical to keeping power consumption down. Any device that travels out to memory for all of its accesses is doomed. And we played a lot with this in the Xeon Phi design and ended up deciding how much caching to put, because caching takes up die area, it takes up power. It's pretty serious. The caches are so large, we could have fit a whole lot more cores on this die if we didn't put so much cache in. But in our observation, we believe that caches are critical for power consumption. And that does differentiate us from the decision some of our competition's doing. And of course, like everybody, every engineer, we think we're right. So you can continue to expect to see big caches from Intel because we believe it solves the power problem better. It's a pain in the butt for programming because it just ups the importance of data locality, but it saves power, and I think that's important. Ultimately, this is one of the slides I love to show. You can log on to a Xeon Phi. You can do a CPU info on it, and I did a tail, and you can see that it has 243, well, it's 244 because they're numbered starting at 0, hardware threads. It's a Linux machine. You log on to it, play with it. Xeon Phi is a lot of fun that way. Because we had a simple vision. Our vision was, when we go multi-core, we wanted to be able to keep a common source base. This is not a program written in 1960. It's probably not even a program written 5 years ago. It's changed. It needs to scale. But as you change a program to take advantage of parallelism, we believe we should be able to keep multi-core and many-core in sync so that the same program runs both places. And that's been proven out pretty well. Now, remember what I said about showing up with a 4-threaded program and your performance sucks? Well, this happens all the time. People will bring their code in, run it on their Xeon, and it works. I've normalized it to 1. They come and run it on Xeon Phi, and they go, God, I just go back to those NVIDIA GPUs. They give me speed up. And we'll look at the code and say, you know, really, you weren't ready for scaling. So this is a real example from a customer that still doesn't want me to say their name, although I think it reflects well on them. They're worried because they feel like this speed up showed that they didn't know what they were doing. Get over it. Everybody has this problem. When you try to scale an app, the performance often goes down instead of up. You scratch your head, and you feel really good when you get the speed up. So this is a real example. They quadrupled their speed, roughly, from a Xeon Phi to after they tuned it, with just a few lines of code changed in this example. They really were missing out on scaling. But we always like to ask them, how does it run on the Xeon now? And it turns out the exact same program recompiled and run on the Xeon ran a lot faster too, because they were changing generically bad things. They were dealing with better parallelism, and in some case, getting their locality a little bit better. This happens to us over and over again. In fact, I can't tell you how often we've had customers tell us, in one meeting, you suck, and we say, well, we'll help you with your program. And the next meeting, they get this, and they say, you guys are awesome. And then they come back after they run it on Xeon and go, that Xeon Phi's not that great. We'll go, it's faster, and your program was written the same way. Anyways, this is it. Obviously, Xeon Phi sometimes, with a program that's highly scalable, can really outdo a Xeon. But the key for us was, can we support the same programming models, same programming languages, techniques? I've taught classes before, and I'll have people raise their hand and say, how do I do this in OpenMP on Xeon Phi? And then I'll tell them. And they'll say, that's the same as what I do on any processor, a Spark, a PowerPC, a Xeon. And I'll say, yes, that was our objective. Some trends here. This is from the top 500. We introduced the Xeon Phi in 2012. And this is how many flops, or how many gigaflops on the top 500 are coming from CPUs, GPUs, Xeon Phis. I think they call it a coprocessor, but it's Xeon Phi in this case. And you can see a trend here. These were zeros for Xeon Phi before we introduced it. That's good. And then afterwards, the numbers have climbed. We think we might be into something. And the #1 system in the world is this. And in fact, our Chinese friends who own this #1 system in the world, they call it neo-heterogeneous computing. We didn't invent that. Our marketing people have gone crazy with it now, but it was the Chinese folks that called it that. And the reason they called it that was they said, hey, my program, I can write it basically the same, Xeon and Xeon Phi, and I can focus on scaling and vectorization, and it applies to both. It's not heterogeneous. It has the benefits of heterogeneous, which is having different design points in your machine, some parts designed for higher levels of parallelism, some for less, but without breaking the programming model, which they would say GPUs do. And I would say that too. And then our next generation, Xeon Phi. So Xeon Phi, the current one, goes up to 61 cores. It was introduced in November of 2012. Nice Landing will be introduced late next year. I guess I can say that now, since we announced the first commercial systems will be available second half of next year. And it's got a few interesting things. One is it becomes a processor. Another thing is that we use an out-of-order processor core we call Silvermont, much more powerful. Today, a Xeon Phi core is about 1/10 the performance of a Xeon core of the same era, 2012. The Amdahl's law effects are horrible. The Silvermont core will be closer to 3x difference instead of 10. And so you'll see some behavior. Some applications will like Knight's Landing a lot better. Their serial portions will run better. We have a high bandwidth on-package memory. Notice I say high bandwidth. I didn't say faster. And it packs 3 teraflops into a chip. So, and we have several more of these on the drawing board, generations. This is a pretty intense design. And the #1 concern is staying ahead of Xeon, I think in a market sense. Obviously, we're concerned with all competition, but designing this to be highly parallel is very important to us. So I'm going to make a quick plug for the Structured Parallel Programming book. And the reason is I really want to stress, despite all that I can tell you about computer architectures, I'll tell you, understanding that some people have been successful at parallel programming already and that they've found algorithms that work. It's sort of like, when I started programming, the cool thing to do was to write a sort that was faster than bubble sorts. And everybody wrote their own sorts, and everybody wrote different things. And of course, parallel computers came along, and what did my professor have me write? Parallel sorts. When you learn that people have already done this and already written a library or already looked into the technique, it's a very powerful way to learn quickly. So what we try to do in Structured Parallel Programming book is hit different techniques that have proven, and we call them patterns. If you've ever studied patterns in computer science, I would say some people really hate patterns because there are some really thick books that make sure that every pattern imaginable is listed. We try to only list the ones that work, that are useful. So if you're worried that we wrote a patterns book, we didn't. We wrote a book that uses patterns that work. Things like map. And I'm actually going to skip over these fast because I cover them in the book, and I was fortunate enough to be able to get a copy for everyone here. Hopefully these are interesting to flip through and think about. But map is a very simple, I can divide up my problem and run it on as many cores as I want because there's no dependence between any of the data, any of the computations. Of course, we talk about reduce because when you're done with that, you might want to reduce it to a single answer. So then you combine them and you get map reduce, and that gets you billions and billions of dollars if you had the good sense to do this and call yourself Google. So Google lives by map reduce, everything they do. Phenomenal what they're able to do with it. Stencils, which I love, great for image processing, but it's kind of like databases. It's like you can do a lot of things with databases. Turns out you can do a lot more with stencils than people give it credit for if you just apply them to a lot of things. Pipelines are actually a favorite of mine. Don't be fooled. Pipelines are highly parallelizable. I've had people tell me, why do you talk about pipelines? Pipelines don't scale. Yes, they do, as long as the things in the pipeline scale. Or you can scale them over time. You can be doing the pipeline if you're pumping data through it. So understanding that you can write a program using a pipeline is a very powerful thing. So anyways, I hope you take a look at that. The book doesn't spend much time on computer architecture, but one of the things about patterns that work are that one of the reasons some of the patterns work is because the way that they're written it both decomposes in parallel and has some concept of locality of data. That's why some of these techniques work. And it can be hidden because I'll say, here's how to do a stencil. And I might not spend a lot of time telling you, well, I did it this way because it decomposes in parallel well, and it operates on local data and goes through it in an organized fashion which fits computer architecture better than if I'm skipping all over. So I love abstractions. So let me wrap up by giving some specific advice, trying to sort out. You're going to go through a lot of abstractions, and I'm going to have an attitude about them. First of all, use abstractions. My goodness, don't go using P threads, and just don't, unless you're implementing an abstraction. And OpenCL is notably missing off my slides. Intel is very involved in OpenCL. We're very good supporters of it. We have great implementations of it. I always want to make that clear, and I'm not a fan. And I'm not a fan because it's not an abstraction, especially when I'm talking to people working in technical computing or HPC. Stay away from OpenCL would be my best advice. The reason OpenCL exists is to give people who are writing things like codecs a way of a small amount of abstraction very close to the hardware so they can write efficient codecs so we can watch our movies at lower power and faster on our laptops and tablets. But in HPC, I don't think OpenCL has a home. That's my opinion. If you want to use it, it's supported on Xeon and Xeon Phi, and it works quite well. It's just not very abstract, and I think programs are not performance portable. I went to a talk on performance portability of OpenCL by Simon. He does a great talk, and I was real fascinated. He was happy that performance portability meant to him that he didn't get more than like 3x variation in performance versus peak when he moved his codes around on different architectures. In HPC, that's death. But for him, it was pretty exciting, and it is in certain places. Anyway, so I'm going to ignore OpenCL other than that. So non-proprietary parallel abstractions. Start with libraries. I wrote BLAS and FFTW. But sometimes I do these talks and I start talking about OpenMP and TBB and Silk Plus, and I get all excited, and I forget to mention libraries. You should always use a library first. You should always, if someone's written a library to solve your problem and it's good at it, just go use it. So whether you're Fortran, C, or C++, just go use. MPI, of course, is a way to worry about distributed memory. So choose a library first. If you're doing cluster stuff, you're probably going to get into MPI. I'd love to say that some of the other technologies are real exciting, but co-array Fortran's kind of cool, PGAS, but just not that widely used at this point. OpenMP or TBB really, I think, are the top choices for node-level parallelism. But they're not too hard to tell apart. If you're in Fortran and C, use OpenMP. If you're using C++, use TBB. It really is that simple. I tried for years to teach C programmers to use TBB, and every time I mentioned templates, people would leave. And they should have. And using directives in C++ is very unsatisfying if you're really writing C++. Now, I'm a C programmer that knows C++, so I don't really write C++ very much myself, not intuitively. But if you're really writing C++ code, you deserve to not use OpenMP. So let me mention a little about TBB. So now I will say TBB book came out in 2007. The structured parallel programming book came out in 12, and Xeon Phi book in 13. We're working on a follow-up book on this that'll come out by Supercomputing. The TBB book came out 2007. It's a little bit dated. It's actually a great introduction to TBB, but we didn't have very many of those books, so we brought a small number of them. And I'm here to tell you, if you're a C++ programmer, keep them by all means. If you grab them and you're a Fortran or C programmer, you might want to bring them back up here and let C++ programmers take them. We just didn't have very many of those books. But it's fine, take them if you use them. But I'll warn you, if you're going to open up and read it's for C++ programmers and then throw it in the trash, give it to someone else in the class this week, please. But we ask a question, how should we extend C++ for parallelism? And we did it with generic programming using templates, a very good C++ thing to do. And then we did a whole lot of other things. And in order to make C++ really work in parallel, we had to do a lot of things, including introducing portable locks and atomics across architectures, OSs. We put a generic interface in place. We open sourced this. It's been ported all over the place, including some folks at Argonne ported it to a Blue Gene. I don't think it got used there a whole lot, but it's interesting. But it's been ported and used a whole lot. It's used in a lot of commercial applications use it. A lot of little open source projects use it. It's very heavily used by companies like DreamWorks and Pixar in their animation studios because they love C++. But we solved all sorts of things. I would say about half of these I hope get absorbed in the C++ standard and we can drop them from TBB, things like portable locks and atomics. They did some in 2011, 2017 they'll do a little more, 2021 maybe a little more, the C++ standard moves along. But there's things, so it's worth taking a look at. If you're a C++ programmer, it tries to solve a lot of problems C++ needs, and it does task-based scheduling using task stealing, very advanced algorithms that if you rewrote yourself, you would be adding a lot of code to your program needlessly. Very effective. So node-level parallelism. So with this, why the heck would there be anything called Silk Plus, which is now in GCC and in Intel's compiler? And the reason's pretty simple. TBB is a library, and there's no way that some of the library features will ever make it into languages. They need to be keyword-based. Really be part of the language to be a compiler. And so maybe Silk Plus is the answer to some of that. But I wouldn't run out. I'd play with Silk Plus, but I wouldn't run out and use it quite yet. Although I think with the GCC implementation, it'll be interesting. So these slides will be available by noon. Hopefully they're useful references. I will say I'm not a fan of proprietary. Proprietary things are very cool to use as investigation. I'm not a fan of encouraging their usage. Of course, two of them up here I happen to mention are NVIDIA's, but that's not really coloring me. The question is, do you understand what you're getting into proprietary? CUDA is very cool. I actually think CUDA is a really intelligent, but it's very specific to NVIDIA's architecture. Always will be. It's not designed to take advantage of a many-core processor, for instance. OpenACC is exactly the same, very, very tailored to GPUs. And our offload mechanism was very tailored to our architecture. There are alternatives. OpenCL looks to be an alternative to CUDA, and OpenMP 4.0 offers, finally, an alternative to NVIDIA and Intel's proprietary offloads. So yeah, just cross them out. They come and go. We do proprietary extensions all the time to investigate space, but driving them back into standards, I think, is very important for all of us. So this is an eye chart. It really is as simple as use libraries if you can, use MPI when it's appropriate. A node, use OpenMP or TBB, depending on whether you're programming in Fortran or C or C++. And Silk Plus, give it a spin if you're interested in what a compiler can do versus TBB. We actually thought about calling it compiled TBB, but that didn't quite work out. But that's the thought behind that. And I would love OpenMP a lot more if it was composable. If you don't know what composable means, I probably should say something, but ideally, you could use an abstraction without any regard to what abstractions are used elsewhere in the program or whether you're inside the abstraction already. OpenMP, you can't do that. If you use OpenMP in a subroutine, but you happen to be inside a parallel region at the time, it will blow up if you try to use OpenMP's full glory. So OpenMP implementations in general don't allow nested parallelism. What actually happens is you're running parallel, you call a subroutine, that subroutine tries to use OpenMP, OpenMP by default ignores that you made an OpenMP request because nested parallelism explodes in OpenMP. It does not in TBB or Silk Plus. It doesn't in any modern abstractions. We blew it when we thought of OpenMP back in 96, 97 when we came out with the spec. We blew it because we didn't understand how important nested parallelism is. Turns out in Fortran and C, not such a big deal. It's a pain in the butt a little sometimes, but we survive. And C++ programs is another reason to hate OpenMP. But other than that, which I put in red, it's a pretty richly supported set of non-proprietary interfaces. So with that, a little bit of architecture, a little bit about what languages to use. Hopefully during the week you get to look at this. Really our job as programmers, this is really hard to understand because there's so much nuances, but is really to expose the parallelism, find it, make it available for systems like TBB or OpenMP or libraries to use, but to stay in parallel mode, not to drop into serial mode. Keep the balls in the air. And the other is to keep track of not moving your data around very much. And that's hard, but it's opportunity. I will tell you that most codes out there, I think, go serial more often than they need to. But how hard is it to fix that? It's not easy, or it would have been done. And most programs are moving data around way too much still. And that's opportunity. So as you're looking at adding parallelism or improving the performance of an application, if you can think about it as, am I keeping all the balls in the air all the time? And don't accept going serial or hitting barriers. Get rid of the barriers if you can. And keeping your data local, reinventing your algorithm. Even if it takes twice the flops to compute something, if you can reduce the amount of data that you move around significantly, you may run much better on every architecture today, including the wonderful ones from Intel. I could take a question or two, and then we can have a break, and then we'll talk about vectorization in more detail.
Very curious about the stencil paper you're referring to from a couple years back. Can you give a reference?
I'm pretty sure in structured parallel programming, yeah, we could find it in here. It's we have a bibliography in here. Oh, I should repeat questions. I was asked for a reference for the ghost pattern stencil. And I can look it up in the bibliography. It's in the bibliography for structured parallel programming. I don't remember the author's name off the top of my head, but if you flip through it looking for ghost, oh, here it is. Oh, yeah, Mark Sneer was one of the authors, but the first one's last name starts with KJ. It's on page 394, about halfway down, Ghosts Cell Pattern, 2010 workshop. That's a really neat paper. It won some great awards and because of its clarity and kind of pulling those concepts together.